Hey Team Bio, your next big unit within our study of ecology is going to be talking about climate change. And the greenhouse effect is the effect that is responsible for climate change. So we're going to be studying how these two relate to one another. Climate change. Okay, I'm sure that you all have heard about climate change and probably studied it before in school. But in our class, we're going to really get into the nitty-gritty of why the climate is changing, kind of the physics behind the greenhouse effect. Okay, so let's start talking about light. Here is the electromagnetic spectrum. This entire image right here, this is showing us the whole electromagnetic spectrum of light. So all of these things are light. This is all light. Light is a complicated thing to study. There's this idea in physics, it's called the wave-particle duality of light, and it means that light sometimes behaves like a wave and it sometimes behaves like a particle. It depends on how you're looking at it, but we're going to be talking about it as a wave here. So when you hear the word light, you're probably thinking about the visible spectrum of light. The small slice of the entire electromagnetic spectrum, which is this whole spectrum here. So this is all the electromagnetic spectrum. And if you look at this spectrum, you'll see that what we talk about when we talk about light, we're just talking about this tiny little slice of the total spectrum. This is the light that we can see. But we can kind of perceive other types of light. When we talk about things being warm or their temperature, we're talking about heat. We're actually talking about infrared light. This is a type of light that we can't see, but we can definitely feel. When we talk about getting a sunburn, we talk about UV light damaging our cells. When you go to the doctor for a broken bone, they're going to barrage you with x-rays, and you're going to be able to see whether or not the bone is actually broken. If you're playing around with radioactive isotopes, then you're going to be experiencing a barrage of gamma rays, which would be very bad for you and potentially give you cancer. But also to the other end of the spectrum, we have radar. We have TV, we have radio waves, Wi-Fi is in here as well. So these are all different forms of light. And what makes them different is their frequency and their wavelength. Radio waves are low frequency and long wavelength. These are pretty low energy waves. And then gamma rays are high frequency and short wavelength. Waves. So you can see here the depiction of the different wavelengths of light, and they're frequent and short in the gamma ray area, and then as we move across the electromagnetic spectrum, they're getting longer and less frequent as we move towards the lower energy area of the electromagnetic spectrum. Okay, so this is all light. What emits light? Well, obviously, the sun is emitting light. The sun is primarily emitting visible light, the light that we can see. But the truth is that all matter emits light. And the wavelength of peak emission is inversely proportional to the temperature of the emitting object. And basically what that can be summarized as is that hot things emit shorter wavelength light, and cooler things emit longer wavelength light. Okay, so the sun, it's pretty hot. It's emitting light in the visible spectrum. Most of the things on Earth are cooler than the sun. And as a result, we mostly emit things in the infrared as heat light. But if you get things hot enough, they can start to emit visible light. So here's an example of something that it's an iron that's been in a fire. So these are cooler. Oh, maybe I should change to white here. These irons have not been in the fire, and they're cooler. They're emitting a type of light that we can't see. They're emitting IR light. Infrared. But if you get this iron hot enough, it's going to start to emit visible light. Okay, so all matter emits light. Hot things emit light that's more over here. Cooler things emit light that's more over here. Okay, here are two examples of infrared cameras, or we also call these sometimes night vision cameras. So the way that night vision cameras work is that they don't actually sense visible light. They sense IR light, also called heat. And they take that IR heat light pattern and they transfer it into being visible light. So here you can see some images of a bird feeding its young in a nest. And we can see the birds at night with this night vision camera because they're emitting heat all the time at night and during the day. And here's another image of an infrared camera trained on people. And just like the birds, these people are emitting IR light, heat light. So this is IR light. And they're emitting it proportional to their body temperature. Okay, so that's main summary of light. They're all different types of light, and cooler things are emitting longer wavelength light, and hotter things are emitting shorter wavelength light, and the sun is in the middle, emitting visible light. We are cooler than the sun, so we emit heat light. Okay, moving on down. Light interacting with matter. When light comes and strikes matter, there are three different things that can happen to it. Light can either experience reflection off the matter, where it hits the matter and bounces off. Oops. Oops, I forgot the U. Hits matter and bounces off. Light can be absorbed when it strikes matter. So here's an example of light hitting matter, and then the matter absorbs light and heats up. So matter absorbs light and heats up as a result. And then the last possibility when light interacts with matter is that actually light cannot interact with it at all. It can pass right through. This is called transmission, when light passes through matter. So light passes through matter. Okay, depending on the different wavelength of light and the matter that it's going to interact with, it will interact differently. Let me give you an example. Okay, here we have a window, a pane of glass. It's impossible to get a sunburn behind a pane of glass because ultraviolet light is absorbed or it is reflected by the glass. Infrared light, also heat light, this is heat, is the same way. It cannot pass through glass, so it hits the glass, it strikes, and it's either absorbed by the glass or it bounces off. The only type of light that can pass through glass is visible light. This makes glass a really good choice for windows because it lets visible light into our homes, and I guess out of our homes as well. But when we have heat on the inside of our houses, so this is heat light, most of the heat is either absorbed or reflected off by the glass. So while we're letting light into our homes, we're preventing heat from escaping our homes. So, we don't have to work extra hard to heat them up. So, glass is an example of a material that is transparent. It transmits visible light, but either reflects or absorbs ultraviolet and infrared light. Okay, so it's a great choice in our homes. We want to keep the heat in, but we want to let the visible light in as well. Okay, here's a picture of an X-ray. When visible light strikes your body, it's sometimes absorbed by your body or it's reflected. So we can't see the insides of our body using visible light because all that light is either absorbed by the outside or it's reflected off the top. So our bodies, bodies absorb or reflect visible light. So using visible light as a way to see inside our body doesn't really work because the light doesn't penetrate through our bodies. X-rays, however, can pass through the soft tissue of our body. So if you look at this image right here, this is an area of soft tissue. And an X-ray, undo. Oh my goodness. An X-ray is transmitted. This means X-rays just pass through the soft tissue of your body. Bones, however, are dense and full of calcium, and this substance actually reflects X-rays. bones reflect X-rays. So this is why X-rays are such a good choice for imaging bones. First of all, X-rays penetrate the outer layer of our body. Soft tissue is transparent to them, so X-rays will pass through soft tissue, but they'll be reflected by bones. So we can image bones using this property. Okay, another example of light either being, okay. I'm going to describe this first. Here we have some lights in a room. And this is visible light. When you're in the room, here, the room is illuminated because the lights are on, and you can see all the things in the room because the visible light coming from the light bulbs. Here we have a wall. And here we have another room. This person is in a room with lights that are on, but the visible light cannot pass through the wall. The wall absorbs and reflects visible light. So the visible light is contained to this one room. This room is dark. There's no visible light. But it contains a Wi-Fi router. The Wi-Fi router is on and it's projecting wireless signals, which are a form of electromagnetic light, somewhere in this region. And the Wi-Fi signals can pass through the wall. Because the wall is transparent to Wi-Fi. So both people get the Wi-Fi signal because the Wi-Fi can pass through materials like a wall. But only this person has Wi-Fi and light because the visible light cannot pass through the wall. So I guess the summary of all of this is that different forms of light interact with different forms of matter differently, depending on the type of light that you have and the type of material that you have. You can either have this happen. Reflection, absorption, or transmission can happen to the light. And so as a result, some forms of light will pass through materials like walls. So Wi-Fi is passing through the wall, but while other forms of light, like visible light, is prevented from passing through the wall because visible light is reflected and absorbed by materials like walls. Okay, so all of this is hopefully going to set you up for a real understanding of the greenhouse effect and why it works the way it does. Okay, I hope this made a little bit of sense. Bye.